This is my Minecraft CPU. The general tour is you've got program memory over here, and it can store 16 lines of code at 26 bits per instruction. Memory is this huge block over here with the 4 rows, so you can store 64 words or 128 bytes. And you've got the register file here, which is kind of used for temporary data storage, as opposed to memory, which is longer term. And then the ALU here, which does different operations on data, such as addition, subtraction, comparison, and or, etc. And then over here you've got this module for incrementing the program counter index and doing branching and jumping. So right now I have the 15-line Fibonacci program loaded in here. And so it takes quite a while to run because I've got the clock cycle set at about 20 seconds, which is really slow. But I calculated it out, and that's about how long this thing needs to execute one cycle because it is so large, and so there's a lot of repeaters in there. So, yeah, I've got the Fibonacci program loaded, and I went ahead and executed it. It takes about an hour to generate 20 terms, but you can see all of the terms down here: 0, 1, 1, 2, 3, 5, 8, 13, 21, etc. All the way up to, you got 16 terms on the first row of memory over here, and then it wraps around over here with the 4 last terms. One really cool thing, so to get the CPU started, you have to load instructions into memory first. Oh dear. I don't know if that was. So to load an instruction into memory, each instruction is 26 bits. So you just store the instruction in a shulker box where beds are 1s and blocks are 0s. And then you can go ahead and just fly up to any one of these lines, and you can go ahead and put your instruction in, and it'll just load it into memory. And then you flip a lever to set memory. So I've just got the Fibonacci program loaded in here right now. And so when it executes an instruction, I have everything kind of color coordinated to show what the different parts of the instruction do. So yeah, there's a 13-bit immediate at the bottom, which is these bottom 13 rows. And they get used for ALU operations, or in the case of branch and jump instructions, they become the line number you want to, or the number of lines that you want to use. The green here can be used as register D in the case of R-type instructions. The yellow blocks here represent register T, which is a kind of flexible register that can be used for any type of instruction. And then the purple blocks here are register S, which is the register that always gets sent to the ALU regardless of what operation you're doing. And then the 5 bits at the top here are the control bits. So I've got this big lattice down here, and it decodes the operation code into actual signals on all of these control lines here. So I've got 1, 2, 3, 4, 5, 6, 8, I think 11 control lines, and they run underneath these glass control tunnels to different areas on the CPU. So for example, this one runs all the way down and goes to the ALU control, I believe. And so you can kind of see how data flows through here. So the operation code gets decoded, updates all of these control lines, which most of them change some multiplexer somewhere in the CPU. And then data flows out from the control line and then out from the register file to gets operated on and then gets stored. You can also load values from memory. Yeah, and to reset the program and get it running again, I have some manual switches you can do here. So this will set the immediate to 0, and then this will turn the jump control on, and then you can just operate the clock once, and that'll reset everything back to 0. And this is the program counter. So I only left space for up to a 32-line program because this is 16 lines and it's already huge. So only 5 bits needed for that. And this is just a full adder that increments it every time, and you can choose between incrementing it by 1 and incrementing it by an immediate that you send in for the branch instruction. And then to actually start the CPU, I'm not going to clear memory. I'm just going to let it overwrite the values that are already there. So you won't see any changes going on in memory, but you will be able to see the CPU kind of running. And then you just send a quick pulse for the clock, and that'll get everything started. So you can see the instruction just jumped from 0 to 1, and you can see it doing stuff. Like I said, it takes about 18 seconds to complete most operations. And the biggest reason for that is that I used a ripple carry adder, and the ripple carry adder takes like 70 ticks to do its thing, which is 7 seconds, which is quite a long time. The memory is also just so large that data travel through the memory takes forever too. But you should be able to see the program counter incrementing there as it marches through the program. And at the end here, I have a jump instruction that will jump back to the beginning of the loop, and then a branch instruction checks if a condition is true, and if the condition is true, then the loop will escape and go to the exit instruction, which is the very last one. And the exit instruction, I have it set up so that it just stops the clock altogether. This is just the easiest way to do that. And you can also manually stop the program by flipping that lever there. So, yeah, you can just see the output from the program memory changing as it marches through the program. And yep. So that's a brief overview of how everything works. I might do more detailed videos later of individual components, but this is kind of your high-level tour.